Welcome! In this session, we'll explore an exciting problem from LeetCode, number 985, sum of even numbers after queries. Let's dive into the problem and analyze how to solve it efficiently. In this problem, we are given two inputs, an integer array called nums and another array called queries. Each element in queries is a pair, val, index. For every pair, the task involves two steps. First, we add the given value val to the element at index in the array nums. Second, we calculate the sum of all the even numbers in the updated nums array. The goal is to return an array answer, where each element represents the sum of even numbers after processing a corresponding query. The input format specifies that nums is an integer array of length n, and queries is an array of integer pairs. The output format is a single integer array answer where the length matches the number of queries provided. Let's explore an example to make the problem clearer. Imagine nums is 1, 2, 3, 4, and queries is 1, 0, 3, 1, 4, 0, 2, 3. Initially, the array nums is 1, 2, 3, 4. Here, the sum of even numbers is 2 plus 4 equals 6. For the first query, 1, 0, we add 1 to nums, 0, making nums 2, 2, 3, 4. Now the sum of even numbers is 2 plus 2 plus 4 equals 8. For the second query, dash 3, 1, we add dash 3 to nums, 1, updating nums to 2, minus 1, 3, 4. The sum of evens becomes 2 plus 4 equals 6. For the third query, dash 4, 0, adding dash 4 to nums, 0, gives nums as dash 2, minus 1, 3, 4, with the even sum now dash 2 plus 4 equals 2. Finally, the query, 2, 3, adds 2 to nums, 3, resulting in nums as dash 2, minus 1, 3, 6, and the even sum dash 2 plus 6 equals 4. As a result, the output for this example is 8, 6, 2, 4. Now, consider another example where nums is 5, 6, 7, 8, and queries is 0, 2, 5, 3, 6, 1, 3, 0. Initially, nums is 5, 6, 7, 8, and the sum of even numbers is 6 plus 8 equals 14. For the first query, 0, 2, adding 0 to nums, 2, doesn't change nums, so the even sum remains 14. Next, the query, 5, 3, adds 5 to nums, 3, updating nums to 5, 6, 7, 13. This reduces the even sum to 6, since 13 is now odd. For the third query, dash 6, 1, adding dash 6 to nums, 1, gives nums as 5, 0, 7, 13, leaving the even sum as 0. Finally, the query, 3, 0, adds 3 to nums, 0, resulting in nums as 8, 0, 7, 13, and the even sum is 8. The output for this example is 14, 19, 8, 8. The output for the second example is 14, 19, 8, 8. Now, let's review the problem constraints. First, the length of nums can range from 1 to 10 caret 4, and the values in nums can range anywhere from dash 10 caret 4 to 10 caret 4. Similarly, the length of queries can also be as large as 10 caret 4, and the values in each query, both val and index, lie within these ranges. These constraints emphasize the need for an efficient solution, especially for large input sizes. For edge cases, if nums contains no even numbers initially, the even sum will start at 0. Additionally, if nums contains only even numbers, queries that preserve the evenness of nums, index, will maintain the even sum. Handling large input sizes efficiently while considering edge cases is key to solving this problem successfully. To begin, one straightforward approach to solving this problem is the brute force method. The intuition here is simple. For each query, we update the specified index in the array by adding the given value. After applying this update, we then compute the sum of all even numbers in the array. This is done by iterating through the entire array and checking which numbers are even. While the brute force approach is conceptually easy to implement, it comes with a significant trade-off. Specifically, the time complexity is O, n asterisk m, where n is the size of the array and m is the number of queries. This is because for each query, we have to make an O, n, pass through the array to recalculate the sum of even numbers. As a result, this approach becomes inefficient for large datasets due to the repeated scanning of the entire array after every single query. While simple, it's not scalable for high-performance scenarios. Now, to address the inefficiencies of the brute force method, we can turn to an optimized approach. The key insight here is that only one element of the array changes with each query, so we don't need to recompute the sum of even numbers from scratch every time. Instead, we start by calculating the initial sum of all even numbers in the array, which we'll call even_sum. For each query, we first check if the current number at the specified index is even. If it is, we subtract it from even_sum because it's about to be modified. Then, we update the number at that index by adding the given value. After the update, we check if the new value at that index is even, and if it is, we add it back to even_sum. This ensures that even_sum remains accurate without requiring us to iterate through the whole array repeatedly. After processing each query, we append the current value of even_sum to our result. This approach is efficient because it avoids unnecessary recalculations. The time complexity is O(n plus m), where O(n) accounts for the initial calculation of even_sum, and O(1) work is done for each query, resulting in O(m) for all queries combined. While this method requires careful handling of even and odd transitions, it is far more efficient and scalable. Given these considerations, the optimized approach is clearly the better choice. It stands out for its efficiency and scalability, especially when dealing with larger datasets or a high number of queries. While the brute force approach is easier to understand and implement, its computational expense makes it impractical for scenarios requiring high performance. The optimized approach eliminates redundant work by focusing only on the parts of the array that change during each query. The key realization, or aha moment, is that only one number changes per query, which allows us to limit updates to the sum of even numbers. This strategy is also scalable, making it well-suited for both competitive programming and real-world applications. While the optimized approach does involve slightly more complex logic, this trade-off is negligible compared to the significant performance gains it provides. To summarize the final complexity, the time complexity is O(n plus m), where n is for the initial setup and m is for the queries, and the space complexity is O(1), since we don't use any additional data structures beyond the input and output. To understand the problem, we are tasked with efficiently processing a series of queries on an array nums. Each query provides a value val and an index. The operation involves adding val to nums index and then calculating the sum of all even numbers in the array after this update. The challenge is to perform these operations in a way that avoids redundant recalculations of the even sum for every query. A straightforward brute force approach would involve recalculating the even sum from scratch after each update, but this can be computationally expensive. Let's break down how the brute force method works. First, we set up our input, an array nums of size n and a list of queries, where each query is a pair of val and index. Then, we initialize a variable current_even_sum to 0. This variable will store the sum of all even numbers in nums. To start, we iterate through the array and add all the even numbers to current_even_sum. This gives us the baseline sum before processing any queries. Now, let's discuss how to process each query in the brute force approach. For each query, which consists of a val and an index, we first check the value of nums index before the update. If the current value at this index is even, we subtract it from current_even_sum because the value is about to change and may no longer contribute to the even sum. Next, we update nums index by adding val to it. After the update, we check the new value at nums index. If this updated value is even, we add it back to current_even_sum. Finally, we store the updated value of current_even_sum as the result for this query. Once all the queries are processed in this manner, we return the list of results, where each entry represents the even sum after processing the corresponding query. This approach reveals some important insights that can help us optimize the solution. First, we can avoid recalculating the sum of all even numbers from scratch after every query. Instead, we adjust the sum incrementally by only modifying it when changes are necessary. For example, we only update the sum if the value at the specified index changes its even or odd status. This condition-based update helps eliminate unnecessary computations. Additionally, the overall time complexity of the approach is worth noting. Initially, we compute the sum of even numbers in nums, which takes O(n) time. Then, for each query, we handle the updates in O(1) time by leveraging these conditional checks. Given m queries, the total time complexity becomes O(n plus m). This is far more efficient than recalculating the even sum for every query, which would have required O(n*m) operations in the brute force approach. To implement this algorithm efficiently, we rely on simple yet effective data structures. The array num stores the current state of the array, allowing O(1) access and updates at specific indices. In addition, we maintain a variable current_even_sum, which dynamically tracks the sum of even numbers in the array. This avoids the need to recompute the even sum after every query. It's also important to consider edge cases. For instance, if all numbers in nums are odd initially, current_even_sum will start at 0 and will only change as even numbers are introduced by the queries. When dealing with large values of val, the algorithm ensures correctness by checking evenness after each update. Finally, if the array or query list is empty, the algorithm simply returns an empty result list immediately, as no computation is needed in this scenario. While the brute force approach provides a clear solution, it's worth mentioning that it can be further optimized in scenarios requiring advanced efficiency. For example, advanced data structures like segment trees can be used to handle some queries and updates more efficiently. However, for most practical use cases, the incremental update strategy we discussed is sufficient. It reduces the time complexity compared to naive recalculations while maintaining clarity and simplicity in implementation. This balance between efficiency and simplicity makes it a robust choice for solving the problem in typical scenarios. Let's break down the solution for LeetCode problem number 985, sum of even numbers after queries. This problem involves processing a series of queries that update an array and calculating the sum of even numbers after each query efficiently. We start by defining a function SumEvenAfterQueries within a solution class. The function takes two inputs, nums, the initial array, and queries, a list of update instructions. Each query consists of a value to add, val, and an index to update. First, we calculate the initial sum of all even numbers in the array using a generator expression. This sum is stored in the variable even_sum. This initialization is crucial because it allows us to update the sum efficiently as we process each query. Next, we initialize an empty list called result. This list will store the sum of even numbers after each query. We then iterate over each query in the queries list. For each query, we first check if the current value at the specified index in nums is even. If it is, we subtract it from even_sum because the value will be updated, and it might no longer be even. After handling the old value, we update the value at the specified index by adding val to it. Once the update is complete, we check if the new value at index is even. If it is, we add it to even_sum since it contributes to the sum of even numbers. Finally, we append the current even_sum to the result list. This ensures that after processing all queries, the result list contains the sum of even numbers after each query. Once all queries are processed, we return the result list as the output. This implementation ensures that we minimize redundant computations and handle each query in constant time, making the solution efficient with a time complexity of O(n plus m), where n is the length of nums and m is the number of queries. Here, we begin by importing the necessary packages and defining the solution class with our method, SumEvenAfterQueries. The goal of this method is to calculate the sum of even numbers in an array after processing a series of queries. We start by initializing a variable, evenSum, to store the sum of all even numbers in the input array, nums. Using a for each loop, we iterate through each number in nums and check if it's even by using the modulo operator. If the number is divisible by 2, we add it to evenSum. Next, we define a result array to store the output of each query. This array will have the same length as the queries array. Now, we process the queries one by one using a for loop. For each query, we extract the value to be added, val, and the index to be updated, index. Before updating the value at the specified index, we check if the current value at that index is even. If it is, we subtract it from evenSum to ensure our evenSum remains accurate after the update. Finally, we add val to nums at the specified index to apply the query update. After updating the value at the specified index, we check if the new value is even. If it is, we add it back to the even sum. This ensures that our even sum reflects all the even numbers in the updated array. Once the even sum for the current state of the array is calculated, we store it in the result array at the corresponding position, which matches the index of the current query. This process is repeated for all queries in the input. After processing all the queries, we return the result array, which contains the sum of even numbers in the array after each query. This implementation efficiently updates the even sum by considering only the affected index, avoiding the need to recompute the sum of even numbers from scratch each time. The use of conditional checks ensures that we only modify even sum when necessary, making the solution both time efficient and easy to understand. To solve this problem, we begin by calculating the sum of even numbers in the initial array nums. In this example, the even numbers are 2 and 4, so their sum is 6. This gives us the initial even underscore sum value of 6. Next, we process each query one by one. Starting with the first query, 1, 0, we add 1 to nums, 0, changing the array to 2, 2, 3, 4. The old value at nums, 0, which was 1, was odd, so it does not affect the even underscore sum. However, the new value, 2, is even, so we add it to the even underscore sum, resulting in 6 plus 2 equals 8. We then append 8 to the result, making it 8 so far. Now, for the second query, -3, 1, we add -3 to nums, 1, updating the array to 2, -1, 3, 4. The old value at nums, 1, was 2, which is even, so we subtract it from the even underscore sum, reducing it to 8, 2 equals 6. The new value, -1, is odd, so it does not contribute to the even underscore sum. As a result, we append 6 to the result, making it 8, 6. Then, for the third query, -4, 0, we add -4 to nums, 0, modifying the array to -2, -1, 3, 4. The old value at nums, 0, which was 2, is even, so we subtract it from the even underscore sum, reducing it further to 6, 2 equals 4. The new value, -2, is also even, so we add it to the even underscore sum, giving 4 plus -2 equals 2. We append 2 to the result, making it 8, 6, 2 at this point. For the fourth query, 2, 3, we add 2 to nums, 3, which updates the array to -2, -1, 3, 6. The old value at nums, 3, was 4, an even number, so we subtract it from the even underscore sum, resulting in 2, 4 equals -2. The new value at nums, 3, 6, is even, so we add it to the even underscore sum, giving -2 plus 6 equals 4. Finally, we append 4 to the result, making the final output for this example, 8, 6, 2, 4. In the second example, the initial array nums contains no even numbers, so the even underscore sum starts at 0. For the first query, 2, 0, we add 2 to nums, 0, changing the array to 7, 5, 5, 5. The old value at nums, 0, was 5, which is odd, so it does not affect the even underscore sum. The new value, 7, is also odd, so again, there is no change to the even underscore sum. We append 0 to the result, making it 0. Next, for the second query, 3, 1, we add 3 to nums, 1, updating the array to 7, 8, 5, 5. The old value at nums, 1, was 5, which is odd and does not affect the even underscore sum. The new value, 8, is even, so we add it to the even underscore sum, resulting in 0 plus 8 equals 8. We append 8 to the result, making it 0, 8, so far. For the third query, -5, 2, we add -5 to nums, 2, updating the array to 7, 8, 0, 5. The old value at nums, 2, which was 5, is odd and does not affect the even underscore sum. The new value, 0, is even, so we add it to the even underscore sum, but since adding 0 does not change the sum, the even underscore sum remains 8. We append 8 to the result, making it 0, 8, 8. Finally, for the fourth query, 1, 3, we add 1 to nums, 3, modifying the array to 7, 8, 0, 6. The old value at nums, 3, was 5, which is odd, so it does not affect the even underscore sum. The new value, 6, is even, so we add it to the even underscore sum, resulting in 8 plus 6 equals 14. We append 14 to the result, giving the final output for this example as 0, 8, 8, 14. To analyze the time complexity of the solution, we start by considering the initialization of even_sum. This step involves iterating through the entire nums array to calculate the sum of all even numbers. Since we need to visit each element in the array once, this operation takes n time, where n is the length of the nums array. Next, we evaluate the cost of processing each query. For every query, the algorithm performs a series of operations. It checks if the number at the specified index is even, updates the number by adding the query value, checks if the updated number is even, adjusts the even_sum if necessary, and finally appends the result to the output list. Each of these steps takes constant time, or O(1). Given that there are m queries, the total time complexity for processing all queries is O(m). This separation into initialization and query processing helps us understand the step-by-step contributions to the overall complexity. Now, combining the time complexities of the initialization step and the query processing step, we can calculate the total time complexity of the solution. The initialization step takes n, and the query processing step takes m. Adding these together gives us an overall time complexity of n plus m. Shifting our focus to space complexity, we observe that the input array's nums and queries are provided as arguments, meaning no additional space is allocated for these inputs. This is considered O(1) additional space. The result list, however, stores one integer for each query, requiring m space. Additionally, the algorithm uses a few intermediate variables, such as even_sum, val, and index, all of which require constant space, or O(1). The total space complexity of the solution is primarily determined by the result list, which grows linearly with the number of queries, resulting in m space usage. Importantly, the algorithm does not use any additional space proportional to the size of the input array nums. Hence, the overall space complexity is m. To put this into perspective, let's compare it with a brute force approach. A naive solution would involve recalculating the sum of all even numbers in the nums array after processing each query. This recalculation would take n time per query, and with m queries, the total time complexity would balloon to n*m. In contrast, the optimized solution avoids this inefficiency by updating the even_sum incrementally with constant time operations. This reduces the time complexity dramatically to n plus m, making it far more efficient, especially when the number of queries is large relative to the size of the array. Analyzing the best, average, and worst-case scenarios can provide additional insights. In the best case, all queries update odd numbers, meaning no adjustments to even_sum are needed. Despite this, the time complexity remains n plus m, as the algorithm still processes every query. On average, we can expect approximately half of the numbers to be even, which means some adjustments to even_sum will be necessary after processing each query. However, since these adjustments are constant time operations, the overall time complexity remains n plus m. In the worst case, every query updates an even number, requiring adjustments to even_sum after each query. Even in this scenario, the time complexity does not exceed n plus m, as the per-query cost is still O(1). This consistency across all cases highlights the robustness of the algorithm's efficiency. Finally, let's provide a mathematical justification for the derived time complexity. Let n represent the length of the nums array and m represent the number of queries. The initialization step, where we compute the sum of even numbers, involves iterating through the nums array once and takes n. Each query involves a series of constant time operations, so processing all m queries takes m. Combining these, the total time complexity is n plus m*1, which simplifies to n plus m. This is the most efficient time complexity achievable for this problem, as every query must be processed individually and the initial sum of even numbers must be computed once. This ensures that the solution is optimal and scales well with both the size of the input array and the number of queries. When solving this problem, there are a few common mistakes to watch out for. First, handling the edge cases for even numbers can be tricky. For example, when a number at a specific index changes, it's easy to forget to check whether the new value is even or odd. If you don't account for this toggle, the sum of even numbers can end up being incorrect. To avoid this, always verify the parity of the number both before and after the update. Another common issue is using a brute force approach. Recomputing the sum of even numbers for every query can quickly become inefficient, especially for large arrays, leading to a time complexity of n*q. Instead, optimize by dynamically updating the sum of even numbers as the queries are processed. Lastly, overwriting the original array without sufficient care can also cause problems. If the input array is needed elsewhere, you may unintentionally disrupt that part of your code. To prevent this, ensure you're making deliberate updates or use a copy of the array if necessary. Now, let's look at two additional pitfalls. In languages like Java or C++, it's crucial to consider integer overflow. When you add large values to an element in the array, the result might exceed the data type's limit, leading to incorrect results. To address this, use appropriate data types like long in Java and include checks for overflow during arithmetic operations. Another frequent issue is incorrect initialization of the even sum tracker. If you forget to compute the initial sum of even numbers in the array before processing queries, the results will be inaccurate. A good practice is to iterate through the array upfront and calculate the sum of all even numbers before applying any updates. This problem is a great example of what interviewers look for when testing your ability to optimize solutions. It falls under the category of dynamic updates with partial sums, where the goal is to avoid redundant computations. Patterns like toggling between even and odd values, while maintaining a running sum, are key concepts to recognize. During an interview, you should also be ready to discuss the trade-offs between brute force and optimized approaches. For instance, you might start with a simple brute force solution to establish a baseline, then demonstrate how pre-computation or additional data structures can significantly improve efficiency. It's equally important to address edge cases, such as empty arrays, arrays with all odd numbers, or scenarios where queries repeatedly toggle a single number. Finally, emphasize the time complexity of your solution. Be clear about why an optimized approach with complexity n+q is preferable to the n*q brute force method, especially for large inputs. This problem also shares similarities with several other LeetCode problems. For example, problem 560, subarray sum equals k, involves maintaining dynamic running sums. Problem 304, range sum query 2D immutable, emphasizes pre-computing values for efficient queries, while problem 307, range sum query mutable, features a similar structure of dynamic updates in queries. Lastly, problem 238, product of array except self, highlights the importance of avoiding redundant computations by leveraging intermediate results. When considering alternative approaches, the optimized method of maintaining an even sum tracker is a strong choice. By dynamically adjusting the sum as queries are processed, you achieve a time complexity of n+q. However, this comes with slightly increased implementation complexity. For even greater efficiency in scenarios with frequent queries, you could explore advanced data structures like segment trees or Fenwick trees. These allow for log n updates in queries, but at the cost of higher implementation complexity, making them more suitable for advanced use cases. Finally, let's touch on the brute force approach. This method involves recomputing the sum of all even numbers after each query. While it's straightforward to implement, it comes with a significant downside. Its time complexity is n*q, which is highly inefficient for large input sizes or numerous queries. For smaller arrays or when simplicity is a priority, this approach might suffice. However, for larger datasets, the inefficiency quickly becomes apparent, making optimized methods a far better choice. Understanding the trade-offs here is crucial, as interviewers often appreciate seeing both approaches and hearing your reasoning for choosing one over the other in different scenarios. Great job! We've summarized the problem, key takeaways, and the techniques used to solve it. Keep practicing and exploring new challenges. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!